On July 25, 2000, Air France Flight 4, so Concorde's pride, raced down a Paris runway, bound for New York, unaware that a single strip of titanium would trigger aviation's most notorious disaster. All 113 lives on board and the jet's legendary reputation were lost within minutes. How could a tiny piece of metal cause the downfall chronicled in How Did This Happen? The Concorde Gonesse disaster, AF4590. And what chain of events turned routine takeoff into catastrophe? The answer begins with what happened beneath the wheels that morning. At nearly 170 knots, the Concorde's left main tire struck a strip of titanium lying unnoticed on the runway. In that instant, the tire's structure, already under enormous stress from the aircraft's speed and weight, gave way. Each wheel on the Concorde spins at over 1,200 revolutions per minute during takeoff, storing massive amounts of kinetic energy. When the tire burst, that energy was unleashed in a violent spray of rubber and wire, fragments flung outward and upward at speeds that could exceed the aircraft's own forward motion. The mechanics of a high-speed tire failure are brutal and unforgiving. The tire's steel cords meant to reinforce the rubber became shrapnel. Centrifugal force drove debris with enough power to punch through aluminum and composite structures. The trajectory of these fragments depended on the exact angle and force of the burst, but the result was always the same. Pieces of tire and wheel ricocheted off landing gear struts, bounced into wheel wells, or shot directly toward the underside of the wing. In the Concorde's design, the space between the tire and the lower wing skin was narrow. With the aircraft loaded for a transatlantic flight, every ounce pressed the wheels harder against the pavement. The collision with the titanium strip triggered a chain reaction in milliseconds. Rubber exploded, cords snapped, and debris became projectiles propelled by physics alone. This raw release of energy set the stage for what followed above the runway, as fragments found their path toward the aircraft's most vulnerable structures. Fragments from the shattered tire slammed into the underside of Concorde's left wing, targeting a vulnerable section known as Fuel Tank 5. Unlike most airliners, Concorde's fuel tanks were built into the wing structure itself, separated from the outside world by little more than thin aluminum skin, less than 2 millimeters thick in places. The violence of the impact did not simply punch a hole. Instead, the collision created a sudden, powerful shock wave inside the tank, a phenomenon investigators called a hydrodynamic pressure surge. With the tank filled to capacity for the transatlantic crossing, there was no airspace to cushion the blow. The incompressible jet fuel transmitted the pressure instantly, forcing the tank walls outward. At the same time, the continuity effect, a twisting, localized deformation of the metal, created zones of intense stress. Multiple ruptures formed almost at once. Fuel began to pour from the bottom of the wing, streaming backward in the slipstream. Within moments, the leaking fuel found an ignition source. Investigators would later point to damaged electrical wiring or possibly contact with hot engine parts as the likely culprit. Flames erupted along the trailing edge of the left wing, visible even before the aircraft left the ground. The fire grew rapidly, fed by a steady flow of fuel under high pressure. Inside the cockpit, warning lights and alarms began to sound, signaling a crisis that was already well underway before the wheels had even lifted. The crew, focused on the critical seconds of takeoff, now faced a spreading fire and a jet that was structurally compromised from the start. In those brief moments, Concorde's fate was sealed, not by a single failure, but by a cascade of forces unleashed in less than a second. Concorde's wheels left the runway with fire streaming from the left wing and warning alarms blaring in the cockpit. The aircraft reached about 200 feet, but never gained more altitude. At this stage, the crew was fighting a battle on multiple fronts. Engine number 2, starved of fuel and engulfed in flames, surged and lost all thrust within seconds. Engine number 1, also on the left, began to deteriorate as heat and fuel starvation took their toll. On the right, engines 3 and 4 continued to provide power, but the imbalance created a strong rolling force that pulled the jet left. The landing gear, damaged by debris, refused to retract. This left Concorde exposed to a drag penalty that would have been significant for any airliner. On Concorde, with its slender delta wings and high-speed design, the effect was devastating. The extended gear increased drag by as much as 20%, demanding more power than the crippled engines could deliver. Instead of accelerating toward the intended climb speed of 220 knots, the jet's airspeed plateaued at around 200 knots. The heavy fuel load, necessary for the transatlantic flight, further reduced the margin for error. Ambient temperatures near 26 degrees Celsius thinned the air, reducing both engine thrust and aerodynamic lift. Inside the cockpit, the crew worked through emergency checklists, attempting to retract the gear and manage the failing engines, all while maintaining control of a jet that was losing both speed and lift. The aircraft was stuck in a narrow performance window, unable to climb, unable to accelerate, and with no safe options left. The physics of weight, drag, and asymmetric thrust had closed the door on recovery, leaving the Concorde trapped just above the rooftops of Gonesse. The Concorde's final seconds unfolded over the rooftops of Gonesse, less than 2 minutes after leaving the runway. With airspeed falling and left side thrust nearly gone, the jet's nose began to drop. The left bank steepened as the pilots struggled for control, but the aerodynamic limits had already been exceeded. At just 200 feet above the ground, the aircraft could neither climb nor turn away. The hotel, Hotelissimo Les Relais Bleus, stood directly in the Concorde's path. Its coordinates, 48 degrees 59 minutes 8 seconds north, 2 degrees 28 minutes 20 seconds east, would become fixed in aviation history. The jet struck the hotel at high speed, wings nearly level, but with a steep downward angle. The impact was devastating. All 100 passengers and 9 crew members perished instantly. 4 people inside the hotel lost their lives as the structure collapsed and fire swept through the building. The crash site, a modest suburban block just beyond the airport's perimeter, was consumed by smoke and flames within moments. Emergency crews arrived quickly, but the destruction left no chance for rescue. From the moment the tire struck debris to the instant of impact, only about 90 seconds had passed. In that brief window, a chain of mechanical failures and physical forces converged with irreversible consequence. The loss of 113 lives in Gonesse would stand as a stark reminder of how fragile the margins of flight can be and how quickly catastrophe can unfold. Inside the BEA laboratories, investigators faced an intricate puzzle. How could a single tire burst bring down a supersonic airliner? Their work began with the battered remains of fuel tank number 5. Metallurgical analysis revealed ruptures that flared outward, not inward, a sign that the force came from within the tank itself. Engineers recreated the event using full-scale tank sections filled to capacity, replicating the exact conditions of the Concorde's final takeoff. When tire fragments struck the test panels at high velocity, pressure waves shot through the incompressible fuel, forcing the thin aluminum walls to split outward at multiple points. This hydrodynamic rupture, a phenomenon rarely seen in aviation, explained the sudden, massive fuel leak. Tracing the root cause led to a small, jagged strip of titanium recovered from the runway. Forensic comparison matched it to a missing wear strip from the thrust reverser of a Continental DC-10 that had departed minutes earlier. Maintenance records uncovered a troubling detail. The strip was a non-standard replacement, fabricated outside manufacturer specifications and attached with improper fasteners. The chain of evidence, lab tests, tank fragments, and maintenance logs left little doubt about the sequence of failure and the origins of the debris. The disaster was not only a matter of physics, but of accountability. Engineers faced a daunting challenge: how to rebuild confidence in an aircraft whose vulnerabilities had been so devastatingly exposed. The first solution took shape inside Concorde's wings. Technicians lined the fuel tanks with Kevlar, a material known for stopping bullets, now tasked with containing fuel in the event of a rupture. This barrier, just millimeters thick, could absorb the shock of tire debris and prevent fuel from spilling into the wing cavity. Alongside this, new burst-resistant tires were fitted, tested to withstand impacts far beyond what the original design had imagined. Electrical wiring and hydraulic lines near the landing gear were shielded or rerouted, reducing the chance that a single fragment could ignite another disaster. These changes required months of analysis, fabrication, and certification. By November 2001, Concorde returned to service, its systems upgraded and its safety record restored in the eyes of regulators. But the world had changed. The September 11th attacks had gutted demand for transatlantic travel. Fuel prices soared, and the cost of maintaining a small, aging supersonic fleet became untenable. Despite technical fixes, Air France retired its Concordes in May 2003, with British Airways following that November. The final flights drew crowds, but the era of commercial supersonic travel had ended, not from a lack of ingenuity, but from the hard limits of economics and time. On July 25, 2000, Air France Flight 4590 became the only Concorde flight to end in disaster, claiming 113 lives in less than 2 minutes. The French BEA investigation traced the accident to a titanium strip, just 43 centimeters long, lost by a preceding DC-10, which caused a tire burst and ruptured fuel tank 5. Despite extensive analysis, the exact ignition source, whether electrical arcing or contact with hot parts, remains undetermined in official reports. The disaster led to mandatory runway debris checks, reinforced fuel tanks, and new tire standards across aviation. Concorde returned to service in 2001, but the combined effects of safety costs and changed travel demand after September 11th led to its retirement in 2003. Memorials now stand at Gonesse and Charles de Gaulle Airport, marking the loss. The evidence shows that even the smallest oversight can have global consequences, and the lessons from AF4590 continue to shape how aviation manages risk today.